Okay, thank you. So yeah, let me start by thanking the organizers for inviting me to be here. I just arrived. I'm really kind of looking forward to chatting with people and uh, to all the interactions. Um, so so over the last 3 days, I'll be giving a series of lectures that gives an introduction to moire materials. And given how active this field has been over the past 6 years, even a full semester or full year would not be enough to give a thorough introduction to the subject. So I will, of course, make some choices to focus on some topics on the expense of others. And two of the main choices I will make is one of them is a very natural and expected choice, which is I will focus on the theory, although this is a very experimentally driven field, because I'm a theorist and because this is a school for theoretical physics. And the second choice I will make is to focus mostly on graphene-based moire systems. And this choice has some personal bias because it's the system I've been working on the most. But there's also some non-personal biases, which is that it was the earliest moire system where all these nice correlation physics was observed. It's also it's still the system which, by volume of the work that was done in the field, it's the system that has the lion's share of the work that was done in the field. And also, it's even from an experimental point of view, it's a system experimentalists like because it's clean and they can do transport measurements easily on it. My talks will be mostly on the blackboard, but since I don't trust my ability to draw self-respecting honeycomb lattices on the board, I'm just using slides for the first 10, 15 minutes where I'll need to draw a lot of stuff. So instead of drawing, I'll show you nicer figures here. So the broad outline of the three lectures will be as follows. So in the first lecture, I will mostly discuss single particle aspects of the system. So basically the symmetries and the band structure, the typical models used to describe the system, which are these continuum models, and also the band topology. For those who have been working in the moire field, which I know some of you have, this may be boring, but at least I'll try to present some slightly different perspective on some of the standard derivations, so it could be useful even for those familiar with the topic. Tomorrow, I will discuss a very interesting kind of subfield that emerged out of the moire problem, which is the study of the so-called ideal or vortexable bands. And this is a statement about the structure, some more fine structure of the flat band wave functions that go beyond the broad topology features that turn out to have a lot of implications on the interaction physics. So lecture 1 will be no interactions at all. Lecture 2 will be a bit of interaction, and lecture 3 will be the strong coupling theory, which is what happens when we add very strong interactions to these systems. So the system that has been the most studied in the whole moire field is twisted bilayer graphene. So let me start by a brief introduction to this system. So this is graphene. So it's a set of carbon atoms arranged in a honeycomb lattice. And here I'm labeling the atoms by red and blue, but they're really indistinguishable. They're all carbon atoms. They're all the same atoms. But because the honeycomb lattice is not a Bravais lattice, it's usually nice to divide it into two sublattices called A and B, usually called A and B. And this is what I mark with the blue and red. And the kind of the main trick in the moire field is to take two sheets of these carbon atoms on top of each other and apply some twist angle. And when you do this, you can see that you get this pattern of dark and light spots called the moire superlattice. And The really magical property is that it's kind of an emergent lattice whose lattice constant you can freely tune. And you can understand this lattice kind of more microscopically by zooming in at different regions. So these light regions are like, if I start from perfectly aligned carbon sheets and I apply some rotation about some site, of course, around the site, I will have the two carbon sheets coinciding with each other. So this is a so-called AA stacking, where each carbon atom from one layer sits on top of a carbon atom from the other layer. But as I go in space, I will also have other stacking configurations, in particular this so-called AB stacking, where one carbon atom from one layer sits on top of a carbon atom from the other, and the other carbon atom sits on top of nothing, on top of the middle of a hexagon. And basically, the moire pattern can be understood as a smooth interpolation between these different kind of special stackings. So I have here in the middle, I have AA, and here on these corners, I have AB. And I get some kind of a periodic pattern or an almost periodic pattern when I do this. Yeah. 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 That's a very good question. It could matter at large angles, but in the limit of small twist angle that I will be studying. Yeah, you can. So you can rotate around the center, or you can rotate around the a site, and this will give generically different stackings. But if you're looking at the limit of small twist angle, it will not matter. So basically, the choice of how you align the two layers relative to each other will become unimportant in this small angle limit, and that's the limit I will focus on. So that's what I will basically talk about next. So let me. Yeah, can I switch to the blackboard for a moment? Yeah. Although I will need the slides again in So one important thing to note about a moire pattern is that it's generally not periodic. Actually, because I have some lattice. I can describe a lattice site by some vector R for lattice A or B. I can write it in terms of basis vectors. So for example, A1 could be this one, and A2 could be this one. Plus, I mean, because I'm labeling not the center of the hexagon, but I'm labeling some corners of the hexagon, I can have some vector tau that basically measures this distance. So this will be the lattice vectors that label the locations of these sublattice points. And now I put another lattice vector on top of it. Let me make this a vector. Now I consider a lattice vector of the second layer, but then I apply a rotation, r of phi, let's say, or r of theta, that's counterclockwise by an angle theta. So I would get generally something like and now I want to find if this pattern is to be periodic, means I want to find an n, m, n prime, m prime, which are all integers, such that there is a given r that is equal to a rotated version, assuming that I align the two at the origin. So generally, this gives a non-trivial Diophantine equation that would only have solutions for a discrete set of thetas. So the moire pattern is only periodic for some discrete set of angles. And there's an expression for such a discrete set, although it's not very important, but I'll just write it in case someone is curious. So the cosine of these angles would be written as 3m squared plus 3mr plus r squared over 2 divided by 3m squared, 3mr plus r squared, where m and r are positive integers. So and they are, I don't know, yeah, and they are co-prime. And one of the difference between commensurate stacking and an incommensurate stacking can be visualized if I just look at the unit cell of one of the lattices, and I fold the lattice points of the other unit cell into that of the other lattice into that unit cell. So for a commensurate stacking, I will get a discrete set, while for an incommensurate stacking, I will get a dense covering. And can I get the slides again now? So yeah, this illustrates the difference I was talking about. So 2.646 is a commensurate stacking, and you can see that as I look at the points of the rotated lattice in the and fold it into the unit cell of the original lattice, I get a discrete set of points, while for incommensurate stacking, I get a very dense set. Now, one thing you can notice is as the twist angle gets smaller and smaller, the density of these points will get larger and larger. So this distinction between commensurate and commensurate stackings will become weaker. And this will turn out to be the limit that will be most physically relevant. And to understand why this is the most physically relevant limit, let me just do a very simple kind of illustration or calculation for the band structure of twisted bilayer graphene. So graphene itself has this following band structure. So the band structure is characterized by two gapless points in the Brillouin zone called the Dirac points, where the dispersion has the energy momentum relation has a linear Dirac dispersion. Now, when I start applying a relative twist between these two bands, if I look in momentum space at the Brillouin zone, this causes a displacement between the Dirac points in the two layers. And as we know, kind of in solid state, when we start from a continuum model and apply some periodic modulation to get a band structure, usually when we get this folding and add the periodic potential, this will cause the appearance of some opening of some gaps. And this can be seen easily if I look at this region. So if I look at this corner, which has one K point from one layer, let me call it K plus, have another K point from another layer, and this midpoint is the midpoint of the two. Does everyone see here, or is it too hard to see? Ah, okay, I can make it bigger, yeah. Okay, Is it visible for the people at the back or? Oh, okay, yeah. So now if I take a cut across this line, and let's say I don't have any coupling between the two layers, then what I will get is at this point, K plus, I will get a Dirac point from one layer. And at the point K minus, I get a Dirac point from the other layer. And the two will intersect in this midpoint, that so-called gamma, small gamma point. So as I switch on a tunneling between the two layers, I will open up a gap here and here. As you can see, if this energy scale is much bigger than this energy scale, then the effect of this gap opening on the overall band structure will be a small effect. So it would open these gaps, but these would generally be small gaps that do not completely restructure the band structure. However, let's see what this energy scale is and what this energy scale is. So this energy scale is very easy. It's the tunneling between the two layers, because that's the effect that causes the opening of the gaps. And to estimate this energy scale, it's easier to estimate this one, so which is a momentum scale. So from this figure, we can see that if the momentum corresponding to the K point of the original graphene, if I call it KD, Dirac, then the length of this line is equal to 2 sine theta half K Dirac. So I have a kind of a line coming from here with an angle where this angle is theta half. So this length is just half of this. So this length is sine theta half K Dirac. So this is this. And crucially, this length depends sensitively on the twist angle. So as the twist angle becomes shorter, this length scale becomes shorter. Now, this energy is very easy to obtain because this is a linear dispersion with a Dirac velocity V Fermi. So this energy is, if I put in all the units, it's, let me write it here. It's h bar V Fermi kd sine theta half. So the point at which the effect of this perturbation would be important is when this object is of the same order as this perturbation. And if I take the typical values that we know, the typical values of these parameters in graphene, this parameter W is around 100 MeV. The Fermi velocity is around 10 power 6 meter per second. This Dirac is 4 pi over 3 root 3, the graphene lattice constant, and the graphene lattice constant is 1.42 angstroms. And putting in all these numbers, I get an angle around 1 degree, which is called the magic angle. So already from this very simple estimate, we know that the interesting physics will happen at a very small angle. And one can understand the emergence of a very kind of small parameter in this problem from the following consideration. It's the fact that the tunneling the in-plane bonds in graphene are much stronger than the van der Waals bonds between two graphene sheets. So the tunneling amplitude of a graphene of an electron in a graphene lattice between nearest neighbors is around 3 electron volts, while the tunneling amplitude between layers is around 0.1 electron volt. So there is a factor of 30, and this is what basically gives you this small parameter. If you write it in terms of radians, that's roughly the same, the value of the magic angle. And so it turns out, and I'll discuss the theoretical basis of this in the next lecture, But it turns out that at this angle, not only the effect of the tunneling between layers becomes very strong, but we get a kind of a resonance effect where these two bands become very flat. And this you can get from kind of a serious band structure calculation. And you see that exactly at this angle, there is a special condition where the bands become very flat. And next lecture, I will explain kind of a model which reproduces this feature analytically. Yeah.
In graphene, the Dirac points are protected thermally by time reversal inversion, right?
Yeah.
So here, what's responsible for opening the gap?
Well, the gap is not open. The gap is open there. The Dirac points are always there.
Okay.
And yeah, I will discuss this point next. And I think, yeah.
So when you start rotating the sample, it seems like the brilliant zone must become much larger. So why is it? Because the unit cell is now very big.
The unit cell is very big, so the brilliant zone is much smaller. Yeah.
Yes. And it seems like you consider that the brilliant zone stays the same, or
no? I mean, this is the brilliant zone. It goes to sine.
Oh, I see. Okay.
Yeah. Any other questions? I think at this point we can get rid of the slides again. And for the rest of the talk, I will not use slides. The fact that interesting physics happens at small angles is very nice, because at small angles, there's a lot more emergent symmetries than at specific stacking. And it turns out that a lot of the microscopic details, like how exactly you align, what point you rotate in the unit cell, doesn't really matter. And one way to see this is the following. Let's start from an aligned configuration and start doing a very small twist around this side. So what would happen is that in this unit cell, the two layers will be essentially aligned. In this unit cell, the position of this point will move a little bit up. In this unit cell, it will move a bit more up, and so on, until you get very close to this point, which is which is not equivalent. So you need to get close to the kind of equivalent point, which is here. Now, at every step of this procedure, you move up by an amount that's proportional to the angle theta times the lattice constant A. So if the angle theta is very small, you're basically moving almost continuously along this line. So to a very, you want me to draw it bigger? Sorry. Yeah. So yeah, we start here, and we start gradually moving. And since this is of order A theta, we're basically moving continuously. So regardless of whether we have a commensurate or an incommensurate stacking, we are guaranteed, after a length that is equal to A over theta, to basically hit an equivalent lattice side. So to be within A theta from an equivalent lattice side. And another way to say this is that for any given theta, there is a commensurate angle that is within distance theta squared. So that's a subleading. Since theta is a small parameter, that's a subleading correction. And this would justify not caring about commensurability at all, and just thinking that all small twist angles are approximately periodic. So we'll think that for small twist angles, we always have a moire, an emergent moire periodicity that is given by this period. Furthermore, you can also see, because from this argument, that if we shift the rotation center, or if we shift the origin of the if we shift the origin of the moire pattern, it doesn't really make a difference, because at small angles we are densely covering the unit cell, so this just shifts the origin of the moire pattern, but it doesn't really cause any substantial difference in the theory. A third thing is that we can, again, look at the details of different stacking and see which stacking leads to some symmetry around which site. But because, again, we are at small angles and all these details shouldn't matter, we can look at very specific symmetric stacking, and from these stacking, figure out all the symmetries of the structure. For example, let's say I do rotate around the center of the hexagon rather than around any generic point. Then I will have two rotated hexagons. Yeah, so they didn't come out very well. So I will have two rotated hexagons, but then it's easy to see that a lot of the point group symmetries of the original graphene would be preserved in this particular configuration. If I took rotation around at different points, I may conclude that these symmetries are not present, but because of this argument that the shifts don't matter, and that at small twist angles, all angles are effectively commensurate, I can basically choose whatever stacking I like that has a high symmetry, and deduce that all of these has to be approximate symmetries of the effective theory in the small twist angle limit. So there was, yeah, if you check the literature, there was, in the early days of the field, there was a lot of discussion about which point you need to twist around and what you need to do, but it turns out this doesn't matter. It makes some symmetries exact and some symmetries approximate, but from a phenomenological perspective, it doesn't matter which symmetry is exact or approximate, as long as you have some specific energy resolution. Any symmetry that's kind of good on that resolution should be a good symmetry, if you care about questions on that energy scale. So since this is not very useful, so what are the different symmetries of this system? So first, there is some simple symmetries that this system inherits from graphene. The first one is SU2 spin rotation symmetry. That symmetry simply holds because graphene has very weak spin-orbit coupling. So if we ignore spin-orbit coupling, we have good SU2 spin rotation symmetry, which means that for all the rest of the symmetries, we can just think of a spinless problem. The second symmetry is that we have seen here that, this was a part of a big Brillouin zone. So let me try to draw again the big Brillouin zone. So I had this line, and I had this small Brillouin zone. But this was a part of a very big Brillouin zone coming from the microscopic system. And what I was focusing on here is the Brillouin zone around the very small region, around this low energy point, close to the Dirac point. But then there is another inequivalent low energy point, which is the other Dirac point. And I will have a similar mini Brillouin zone, but there is no really low energy process that couples these two, because you'd need to have a lot of small scatterings to get from one to the other. So to a very good approximation, the two valleys are decoupled. There's no direct tunneling terms between them. So I have a U1 valley charge conservation. And I'll choose the valley Pauli matrix to be tau. So this is a U1 symmetry generated by tau z. There's one symmetry that is usually assumed, although it is broken by some, it can be broken by some terms like phonons, which is if you think that the valleys are not just decoupled in terms of charge, but also in terms of spin. So you can think that you have a separate SU2 spin rotation symmetry per valley. And at least on the level of the single particle theory, this is always assumed. Next are the spatial symmetries. And as we said, we can look at the very high symmetry configuration. So if we look at this honeycomb, we look at a version that's twisted by an angle theta half, let's say relative to the x-axis. We twist one by an angle of theta half and one by an angle of minus theta half. Then the resulting configurations still have the six-fold symmetry of the honeycomb lattice. And I will find the convenience to split the six-fold symmetry into a two-fold symmetry and a three-fold symmetry. So first, I will have a C2Z, which is a two-fold rotation. And you see that the two-fold, so if this is sublattice A and this is sublattice B, a two-fold rotation maps A to B. So it has to, if I denote the sublattice Pauli matrices by sigma Z, it has to anti-commute with sigma Z. Anti-commute. Also from this picture, this is valley K, this is K prime, K, K prime. So two-fold rotation maps K to K prime because yeah, so it's 180-degree rotation. So we get C2Z, tau Z, also anti-commute. And it has to commute with time reversal symmetry. I haven't read time reversal symmetry. So these, one choice of C to Z that's compatible with these is to take C to Z equals sigma x tau x. Fifth symmetry is time reversal. So time reversal flips valleys. And because it's spinless, it has to square to +1. So one possible choice is tau x complex conjugation. Then there is there's threefold rotation. And again, you can deduce the form of threefold of C3 from its relation to different symmetries. So for example, it has to commute with time reversal. It has to commute with twofold rotation. And also, just from here, under threefold, A maps to A, and the valley is unchanged. So it has also to commute to sigma Z and tau Z. And this leads to where the sign here is related to other conventions. So I'm fixing the convention. There is two last symmetries, which are, let me do this. Yeah, it's anti-commutator because it flips sigma Z. So it flips sublattice and valley. So it has to anti-commute. So yeah, if it preserves a certain, like if it preserves the sublattice or valley, it would commute. If it flips, it anti-commutes. And that's kind of how I construct the symmetries. So there's two last symmetries, which are not really independent, but so one of this is a reflection around the x-axis, and the other is a reflection around the y-axis. Now, these are symmetries of graphene itself, but in the twisted structure, you have one graphene rotated like this, another graphene rotated like this. So under a reflection, they map into each other. So this is a reflection combined with interchanging the upper and the lower layer. So you can think of it actually as an in-plane rotation, a rotation by 180 degrees about some in-plane axis. And yeah, again, we have to be careful about which symmetry is which. So since I'm choosing the convention where the carbon-carbon bonds are vertical, then reflection around the x-axis flips sublattice, but it doesn't flip the valley because, this valley and this valley are the same. While a reflection around the y-axis does the opposite. So one of the two, so so one of the two mirrors will be a tau x mu x, where mu is a layer Pauli matrix, and the other will be sigma x mu x. So now I want to derive an effective single particle Hamiltonian describing the system just based on these symmetries and based on one extra simple assumption. So this is called the Bistritzer-MacDonald model. And I mean, in the original derivation by Bistritzer-MacDonald, they kind of tried to derive it from somehow phenomenological or first principle considerations. I want to just derive it based on symmetries. So the model, so what I will write now is a model for a single valley, because the two valleys are related to each other by time reversal. And the model has a very simple form. It's one graphene layer. And another graphene layer taken in the continuum approximation, which means I take the dispersion close to the Dirac point where I can just linearize it. If you want to do things very carefully, you need to rotate the Pauli matrices different in the two layers. So you have to do plus theta half here and minus theta half here. But at small angles, this is unimportant. So you can drop. And the other part of the model is the moire tunnel. So this is a Hamiltonian in the layer space. So this is layer 1 and 2. And each block of these is a 2 by 2 matrix in the sublattice space, because I still have this sublattice degree of freedom. So this is Pauli matrix. This is a vector of Pauli matrices that is in the sublattice space. Now, these T of R's should satisfy the moire periodicity, but from the way I wrote the Hamiltonian, there is a slight subtlety in how the moire periodicity acts. And to see this, let's just consider switching off these terms. If I switch off these terms, I know what this Hamiltonian, I know the eigenfunctions of this Hamiltonian, the Bloch states. So one Bloch state comes from one layer, and it should be 0 here, and e power I k minus k plus dot r, where k plus is the Dirac point of the first layer. Because this guarantees that when I act with this object, I get a 0 exactly when k is equal to k plus. So this is psi 1. Then there is an eigenvector for the second layer, which has k minus dot r. So they satisfy slightly different properties under translation symmetry, which means when I switch on T and I want to mix them, I want to have a general Bloch state that transforms under translation as e power I k minus k0 dot r v of r psi k of r, where k0 is the average. So it's the midpoint of k plus and k minus. And remember, so I had this drawing, and I had, so this is k plus, and this is k minus. And this V of R is just the diagonal matrix that has e power minus I delta k dot R, e power I delta k dot R, where delta k is the difference. It's k plus minus k minus. Now this delta k is, first it's proportional to sine theta, because just this length is proportional to sine theta because this was theta half. So this is simply sine theta half kd 0 minus 1, and it's usually called, this object without kd is called q1. So it's this vector that connects k plus to k minus. And it's typically also, we typically denote the vectors related to it by rotation symmetry by q2 and q3. So from this, we see that the Hamiltonian has to satisfy the following under translation, which is that it transforms. So this is basically the kind of the form of the translation symmetry, but it has some phase factors that are different for one layer and the other. So it's a translation symmetry up to some unitary. And from this, we can actually deduce the properties of T of R under translation. So T of R has to transform by minus 2 delta k of R. So the end of all this discussion is this up. Is that we can expand T of R in Fourier components, but they all have this shift Q1 plus G, where G are reciprocal lattice vectors of the moire lattice. So the next approximation is to take the leading harmonic. So notice that this Fourier component T of G corresponds to momentum Q1 plus G. So remember, this is Q1. So the shortest moment, there's no, this is not the only momentum with the minimal length. There's also two other momenta which are related to it by rotation symmetry, Q2 and Q3, which are basically Q1 plus a one reciprocal lattice vector, this, which call like G1. And this is Q1 plus another reciprocal lattice vector, which is G2. So if I keep this leading approximation, I will have some L1, 2, 3, TL e power minus I BL dot R. So this gives me a model that has, so TLs are not Hermitian because I have T and T dagger. So this, and each TL is a 2x2 matrix. So these are 3 complex 2x2 matrices, 12 complex parameters. And my job now is to use all these symmetries to reduce this to a small number of parameters. And that's usually the logic we employ, not only for twisted bilayer graphene, but for any system. We try to impose as much symmetries to reduce this number of parameters. So first, threefold symmetry relates the different TLs. So we can show that TL is equal to so now I can just focus on T1. Then I can use my, which flips the sign of Q1 and flips the sublattice and layer to impose an extra restriction on this T1. So this is with my. I can use another symmetry, which is C2T, to impose another restriction, which is and applying all of these restrictions, I get that T1 depends only on 3 real parameters: W0 sigma 0, W1 sigma x plus I, W3 sigma z. So this is almost the Bistritzer-MacDonald model, except for one thing. But first, I just want to notice one thing about this general procedure. Although you could, of course, like do the regular Bistritzer-MacDonald derivation, but this procedure would allow you to know if some of these symmetries are explicitly broken in some system, what extra terms could appear in the model. So that's kind of the advantage of doing things this way. So we have now a model that depends on three real parameters. Oh, yeah, sorry.
Very small question.
Yeah.
What's the BL you've written? Did you write the definition of that?
This is the old. Sorry. This is Q. Sorry. Yeah, this is Q. Sorry. Now, it turns out the Bistritzer-MacDonald model has an extra, possibly accidental symmetry, which is a particle hole symmetry. This is a symmetry that appears in most ab initio derivations of the effective model for twisted bilayer graphene, but I do not know of a simple kind of way to reason about it from the structure. And this is a particle hole symmetry. So it flips sublattice, flips layer, and as you know, this is a unitary particle hole symmetry, but unitary particle hole symmetries, when you wanna act with them on single particle Hamiltonians, they are attached to complex conjugation because so it's this operator H. It's implemented like this. Or H transpose. I also want to mention that so there's also a lot of discussion in the literature about particle hole symmetry in this system. In the experiment, particle hole symmetry is clearly broken, but all the kind of standard models we use for twisted bilayer graphene either have this symmetry either built in or emerging. So it's not very well understood why the experiment breaks this so much. But when you just derive the model under these kind of natural symmetries, it doesn't really have this symmetry, and you are allowed to have this extra term. Yeah.
Apply when theta is small, right?
Yeah.
And in practice, how small would you take theta to be? You give a reference.
Yeah. So I think any term that breaks these will be small up to subleading orders in theta. So if your typical energy scale is few MeV, then it's few MeV times theta, because the few MeV is already reduced due to theta. So it's if it's 10 MeV, that would be 0.1 or 0.05 or something. No, the energy scale. So I'm talking about if theta is 1 degree. So you're asking how big theta should be for this approximation to hold. It's a quantitative question. So at some sufficiently large theta, you can see effects of commensurability. I don't know experimentally if this has if the whole range of thetas have been mapped and people have seen very clear evidence of commensurability. But I mean, the issue also is that at large theta, there is no easy signatures in transport of the twisted structure at all, because so for example, people have looked at this 30-degree twist system because it has an emergent 12-fold symmetry and looks like a quasi-crystal, like really a 12-fold quasi-crystal. So people were excited about this. But in that system, the point at which the two Dirac cones intersect is very high in energy, 1 eV, and this is inaccessible by gating. So you cannot see anything in transport. So you could see some signatures, but they just look like two decoupled Dirac cones. So your question is, are there intermediate theta where I can still gate and feel the effects of the coupling between the two, but I can also see the difference between commensurate and incommensurate? And that's a good question. I don't know. I don't know of experiments that have seen this very clearly. So if we assume particle symmetry, we can remove this term. So we have a model that depends on two parameters. In the original work by Bistritzer and MacDonald, they just assumed these two parameters are equal. However, later work has found out that there is a reason to assume that this parameter is smaller than this one. And that reason is the following. So you see this parameter multiplies sigma 0, and this parameter multiplies sigma x. So this corresponds to tunneling between the same sublattice, between the two layers, while this corresponds to tunneling between opposite sublattices. Now, it turns out that when you look at the moire pattern, so this will control the tunneling in the regions that are AA, where the two sublattices sit on top of each other, while this controls the tunneling in the AB regions, where one sublattice sits on top of the other. And it turns out that energetically, graphene likes to be AB stacked rather than AA stacked. So when the lattice is allowed to relax, it grows these AB regions and shrinks the AA regions. So this effectively reduces this one and pushes this one up. And the ratio that people have, like, yeah, so there's a range of values of this ratio in the literature. It's usually between 0.5 and 0.8. So the last thing I want to talk about, which turns out actually to have a lot of implications for the interaction physics, is band topology. So when I look at the band structure that I get out of the Bistritzer-MacDonald model, so of course, the first thing I would notice is that I have these two very flat bands around charge neutrality. But these flat bands are not very innocent. So the properties of the wave, the wave functions have some very unusual topological properties that actually has important implications for the interaction physics. And to understand this, let me take the wave functions of these two bands. Let me call them, psi alpha k, where alpha now is 1, 2, and labels these two bands. And let me take the Bistritzer-MacDonald Hamiltonian and project it onto this basis. Yeah? Okay. Is this good? Yeah, thank you. So clearly I can have, so when I say I take the space of bands psi alpha beta, I'm allowing myself to take any linear combinations of these states. So they don't really have to be energy eigenstates, as long as at the end I'm projecting everything, I'm projecting the Hamiltonian onto this basis of bands. Of course, this Hamiltonian depends on the basis choice and on the gauge, on the choice of gauge of these wave functions, but its eigenvalues will give me the spectrum. What I'm interested in in other properties of this Hamiltonian. Now, this is a 2 by 2 Hamiltonian, so I can choose to write it like this. Where B of k is some vector. I'm interested in the properties of the wave functions, so for that purpose, this term doesn't really matter, so I can get rid of it. Actually, if I have particle symmetry, I can also kind of remove this term. But importantly, I can make a gauge choice such that the combination. So I have these two symmetries, which is twofold rotation, which flips sublattice and valley, and time reversal symmetry, which flips valley. But I want a symmetry that acts within the valley because I want to restrict things within the valley. I'm looking at this 2 by 2 Hamiltonian within the valley. So I will combine C2 and time reversal. And the symmetry I get, I can represent as sigma x times complex conjugation, while now sigma x is the labels this 2 by 2 space. There's a reason I'm using the same Pauli matrix as the sublattice, because this basis turns out to be related to the sublattice basis, to the microscopic sublattice basis. But for now, it's just an abusive notation. So if the symmetry has this representation, then it will, because the sigma x and sigma y are even under this, but sigma z are odd, it means that the z component of this vector has to be 0. So the Hamiltonian, this 2 by 2 Hamiltonian, is described by an in-plane vector, by a two-dimensional vector that lives in plane. At the points where this vector is 0, which actually turn out to be these direct points, so this vector is 0 at these direct points, but away from these points, it's a well-defined vector, and because it's a 2D vector, I can define a winding for it. So I can look at the Brion zone, and I have some 0 points, and away from these 0 points, I can take a loop and look at the winding of this vector. And this winding will give me a z invariant, would give me an integer. So I can ask the question, whether I have any kind of net non-trivial winding around the Brion zone in this system. So typically in systems we encounter like graphene, which have this symmetry, we have some gapless points. And we can, like, for example, if we have a Dirac point, we can show that it's associated with a 2 pi winding of this vector, so a full unit of winding. But usually the net winding cancels over the Brion zone. For example, in graphene, we'll find that we have 2 Dirac points. One of them has a winding of 2 pi, and the other will have a winding of minus 2 pi. However, something very unusual that we notice about this band structure is that the 2 Dirac points have the same winding. So if we keep expanding this loop and make it to include the full Brion zone, we find that we have a net winding. And what this means is that it's actually impossible to find a gauge for these wave functions such that h of k is both smooth and periodic. So here I'm assuming that h of k is smooth, but then I found it cannot be periodic because it has a net winding over the unit cell. And you can understand the fact that these 2 points have the same winding from the fact that they came from the 2 copies of the same Dirac point. So I had a system. I have 2 layers. I took the same Dirac point from both layers, which have the same winding, and I just combined them into one Brion zone. And so I get, in the same valley, I get the same winding. In the other valley, I get opposite winding. But now, since I'm thinking of the 2 valleys are completely decoupled, I'm looking at each valley separately. And in each valley separately, I have this non-trivial winding. This non-trivial winding is related to an invariant that can be defined for any a two-band system with a real structure. So C2ZT gives me a reality condition on the Bloch states because it acts by complex conjugation and acts locally in momentum. And so this invariant is related to the Euler class of this two-band system with this real structure. But the important thing I want to get out of this invariant is are two things. First, this invariant implies the existence of so-called Vannier obstruction. It means that I cannot really describe this space of band. I cannot find the linear superposition of these wave functions that gives me a basis of exponentially localized states where the symmetry acts naturally. And the way to see this is by contradiction. To say, let's assume I can write the Bloch states as the Fourier transform of some Vannier states, where these are, so if I define the real space wave functions, these objects are exponentially localized functions. They're exponentially localized around site R. Now, if I have this, I can substitute in this expression and find that H alpha beta k is sum over R prime, e power minus I, k minus k prime. No, sorry. Now, this wave function is exponentially localized around site R prime. This wave function is exponentially localized around site R, and this Hamiltonian is local. So this whole object decays exponentially in R minus R prime. And the Fourier transform of a function that decays exponentially in R minus R prime will be periodic and smooth in K, which leads to a contradiction. So I know that this wave function cannot be smooth and periodic in K. So it means that I cannot really find any exponentially localized basis for this system. There is another way to understand the topology in the system, which is to use the so-called non-abelian Berry curvature. So the non-abelian Berry so you define a connection that is kind of a matrix in this band index in the usual way. And then you define a corresponding curvature, which will be a 2 by 2 matrix. Then you will see that, because this is like Berry curvature. So how does Berry curvature behave under different symmetry? Berry curvature is like magnetic field in momentum space. So it's odd under time reversal, but it's even under rotation symmetries. So like the whole conductance, for example, is even under rotation symmetries and odd under time reversal. So this object will be odd under the action of C2T. And remember, C2T acts locally in momentum. So if I expand this in terms of Pauli matrices, I will find that the only odd Pauli matrix under the action of this symmetry, which is sigma x times complex conjugation, is sigma z. So I see I can find f of k as omega of k for some function times sigma z. And the quantization of the Euler invariant tells me that this Berry curvature will be quantized as a Berry curvature, and then an actual Berry curvature is expected to be quantized, which would tell me that I have actually two bands. So I can think of these two bands in a different basis, the basis that diagonalizes this Berry curvature, as consisting of one band that has a Berry curvature omega of k, abelian Berry curvature omega of k, and another band that has an abelian Berry curvature minus omega of k. And there's a simple argument to see that to get two Dirac points that has the same winding, this Berry curvature has to integrate to 1. It's to give me U-Chern number 1. One thing to note is that if you actually look at this matrix, you see that the Berry curvature has the sigma z. So the basis that diagonalizes the Berry curvature is the sigma z basis, but the Hamiltonian has sigma x and sigma y. So it's off diagonal in this basis. So if I want to go to this basis that diagonalizes the Berry curvature, the Hamiltonian will look like this single particle Hamiltonian will look like a tunneling term that connects these two opposite Chern bands. I want to mention two things about the Vannier obstruction here. So there's a few ways there's an alternative approach to see that these bands have a Vannier obstruction, which is something called the symmetry indicator method. I will not discuss it, but I can provide a reference for those interested. So the symmetry indicator method, what it does is it says the following. It says we need to construct some exponentially localized basis of two orbitals per unit cell. But if this system if this basis has to respect all symmetries, there's not that many places we can put these two orbitals. We can either put these two orbitals in the middle of the hexagon, which is a so-called AA site. Actually, at first glance, this seems the natural option, because if you look at the charge density for the wave functions that give you the flat bands, you find that the charge density is actually concentrated on these AA sites. And also, if you do the STM, if you look at the experimental charge density, you'll see that it's concentrated on these AA sites. But it's easy to see that if you try to put the two orbitals at the AA sites, you will never be able to get the right band structure. So you will always get an extra band touching at gamma. Another option is to put the orbitals in the honeycomb site. And that already is a bit weird choice, because the charge density is really concentrated here. So if you want to build an orbital whose charge center is here, it has to be formed as a linear superposition of the charge density from these three sites. So it has to have the orbital here has to have weight. Most of its weight will not be at this side, but will be at these three sites. And these kind of orbitals are called fidget spinner orbitals. It turns out with an orbital like this, you can reproduce something that looks like this band structure, but you will get the wrong winding. So you'll get the two Dirac points to have opposite windings. So also this doesn't work. Now, you can decide to do something, which is to say it's very important to construct exponentially localized Vannier functions, that I will kind of sacrifice some of the symmetries. In the sense that it's known that in a 2D system, you can always construct exponentially localized Vannier functions as long as the total Chern number vanishes. What this means is that you can construct exponentially localized Vannier functions in the system, but some of the symmetries will be represented unnaturally in a non-local or unnatural way. And the symmetry that at least some of the models in the literature, so-called Kang-Dvafik model, tried to, they did that and built an interactive model out of it. And the symmetry they sacrificed was C2T. The initial argument was that C2T is an emergent symmetry, so it doesn't matter. But as I'm discussing, emergent, there's no real difference between exact and emergent symmetries. So when you do this, you sacrifice some aspect of the physics in the sense that some aspects of the physics will become very non-transparent because there is a symmetry of the problem that your representation is implementing in a very unnatural way. One other thing, which is, if you read papers about twisted bilayer graphene, that's something you may encounter, which is that this kind of funny obstruction is called fragile. And what this means is that you can actually add more orbitals. And although these orbitals are trivial, they are kind of atomic orbitals. If you combine them with the flat bands, you can actually write a tight binding move where you can find a Wannier basis that describes all the physics. There is several ways to see this. One of them is to notice that this Euler class is only a Z invariant for a two-band system. So basically, the manifold described by a two-band system is S1, and this gives you a winding. But when you look at more bands, this manifold is not a manifold that gives you an integer winding. So once you add more bands, you can actually get rid of the topology defined by this Euler class. There's a more direct way, which is to just construct these bands explicitly and show that you can combine the flat bands with other bands and get a tight binding model. And that was, of course, done in the literature. There's even a third shortcut, which is that in general, whenever in 2D, if you don't really have edge modes, you can always deduce that the obstruction is fragile. So the only obstructions that cannot be really removed by adding trivial degrees of freedom are the ones associated with anomalous surface states. So I think this is a good point to stop. Tomorrow I will discuss a model, a special model. It's a bit artificial, which is called the chiral model, but where a lot of the properties of the bands of the Bistritzer-MacDonald model can be illustrated very vividly. And this model has an extra very interesting property, which has several names like ideal band condition or vortex ability. And it turns out that that condition can lead to very powerful implications for many body physics. So yeah, that's the end of my talk. Thank you for your attention.